Linear algebra, lecture 7. And we've been talking about matrices. So an m by n matrix, A, this is my shorthand notation, Aij in parentheses. This is the matrix which has m rows and n columns. And in general, Aij, this is the entry in the ith row and the jth column. And we know how to add matrices. That's easy. You add matrices of the same shape. Multiplying matrices is a little bit trickier. And in general, you cannot multiply two rectangular matrices of the same shape. You can multiply matrices if the number of columns in the first equals the number of rows in the second. So if A is an m by n matrix, and B is an n by p matrix, so the matrix A has n columns and the matrix B has n rows, then you can multiply. A times B, you get a matrix I'll call C, which is an m by p matrix. And let's take the simplest case, maybe when m and p are equal to 1. So you have A is a 1 by n matrix. That means one row, n columns. It's just a row vector. Let me just write it as A1 up to AN. And B is an n by 1 matrix. So B has n rows and 1 column. So in this case, this is a row vector, if you like. This is what we would call a column vector. And A times B, this row times this column, you take the sum of the first coordinates, second coordinates, and so forth, and add. It's A1, B1, A2, B2, up to AN, BN. That's how you multiply a row into a column. Can't do it the other way around, but you can multiply a row into a column. So for example, if you had 3, 7 minus 8 times 2 minus 5 minus 1, this row times this column, you have 2 times 3, 7 times minus 5, minus 8 times minus 1. So this is 6 minus 35 plus 8. Minus 21. And how do you multiply in general a matrix by another? A times B. This is m by n. This is n by p. So this is some matrix C. And what is the ijth component of C, of the product? So you get Cij by multiplying the ith row of A times the jth column of B. That's the formula for matrix multiplication. You have an m by n matrix and an n by p matrix, and you get the ijth coordinate of the product is the ith row of the first times the jth coordinate of the jth column of the second. And since this has number of coordinates here equals the number of coordinates here. So just as an example, if I have, I don't know, 3, 7 minus 8 2, 1, 0. So this is a 2 by 3 matrix. Say I want to multiply it by a 3 by 2 matrix. Maybe 2 minus 5 minus 1, 1, 2, 3. So a 2 by 3 times a 3 by 2, it's like the 3's cancel. This is going to be a 2 by 2 matrix. What goes into the first row, first column entry? First row times the first column. I actually calculated that up here. That's minus 21. What is in the first row, second column entry? It's this row times this column. 3 plus 14 is 17. Minus 24 is minus 7. Second row, first column. Here's the second row, first column. 4 minus 5 is minus 1. Second row, second column. 2 plus 2 is 4, plus 0 is 4. So that's what I get. This is the matrix. This is the product matrix. Okay. Any questions about this? You have to do a lot of calculations by hand to become familiar and adept at this algebraic operation.
I have a question.
Yes, go ahead.
The last part where you got negative 21, how did you get that?
This row times this column, which is the calculation I had done at the top of the page. Same row in the same column, minus 21.
Oh, okay. Thank you.
There's also an operation on matrices called the transpose. So you get the transpose of a matrix by interchanging the rows and the columns. So suppose A is the matrix 3, 7 minus 8, 2, 1, 0. So A transpose, which I write with the superscript T, if this is a 2 by 3 matrix, this will be a 3 by 2 matrix. And how do I get it? I take the first row of A and I make it the first column of A transpose. I take the second row of A, I make it the second column of A transpose. All right. Is a question? Okay. Now, in particular, if I take a vector, a column vector, say this is maybe 7, 2, 8, minus 1. This is also a matrix. It's a matrix with one column. This is like a 4 row by 1 matrix. So I can take its transpose. And this will be a 1 by 4 matrix. 1 row, 4 columns. So this first column, 7, 2, 8, minus 1 becomes the row 7, 2, 8, minus 1. So a vector is just a matrix with 1 row or 1 column, and you can take the transpose of a vector. The transpose of a column vector is a row vector. So in fact, if I'm given 2 vectors, say V is 7, 2, 8, minus 1, and W is 3, minus 2, 0, 5. I can look at V transpose W, because V transpose is now this row vector, 7, 2, 8, minus 1. And W is this column vector, 3, minus 2, 0, 5. And I can multiply them now, because I can multiply a row vector times a column vector. I get 3 times 7 plus 2 times minus 2. plus 8 times 0 plus minus 1 times 5. So this is 21 minus 9, or 12. So if I'm given two vectors, v and w, of the same dimension, two column vectors, v transpose w is, I can multiply them, I get a number. And this is sometimes called the, in calculus, this was called the dot product. Sometimes it's called the scalar product of the vectors. Sometimes it's called the inner product of the vectors. But if you have two vectors, v transpose w is a number, is a scalar. Okay. Now you can rewrite any system of equations in matrix form. So suppose you have the equations a11x1, a12x2, and so forth. a1n xn equals b1. You have m equations and n variables, am1 x1, so we have m equations in n variables. So we have what is called the matrix of coefficients of these equations, which is just the matrix that you get by taking the coefficients of all the variables. This will be an m by n matrix. So we just take the coefficients of the left-hand side of the first equation, and that gives you the first row of your matrix. You do that for every row. The last row is am1, am2, up to amn. Right. So this is the matrix of coefficients of the equations. I can take the column vector x of variables x1, x2 down to x sub n. So I can multiply a times x. This is m by n. This is n rows, one column. What do I get? a11, a12 up to a1n, down to am1, am2 to amn, times x1, x2 down to x sub n. This is m by n by 1. The product will be m by 1. It'll be, well, what will the first coordinate be? a11 x1 up to a1n xn. Exactly this left-hand side of the first equation, all the way down to am1 x1 up to amn xn. And if I let b be the column vector of the numbers on the right-hand side, b1, b2 down to b sub m, the vector equation ax equals b, setting this equal to b1 up to bm, this is just the vector. This vector equation is exactly the same. It just is a vector way of writing the system of m equations and n variables. This is because it says that this column vector equals b1 up to b sub m. So the first coordinate equals the first coordinate, and so forth. So this is not yet anything particularly useful. It's simply a concise way of writing, or an equivalent way of writing, a system of equations in vector form. Okay.
I have a question.
Yes.
Where you written ax equals b, what is that referring to?
A is the matrix of coefficients of these equations. X is this column vector. B is this column vector. It comes from the right-hand sides. Let me do an example.
Mhm.
Let's see if I can find an example in the text. Makes things a little bit easier. All right, so suppose we had 9x plus 11y equals -1. 5x plus 6y equals -3. So, sorry, equals 3. There's a typo in the book where it has -3 instead of an equal sign. So, since I only have two variables, I'm using x and y instead of x1, x2. So the matrix of coefficients will have the coordinates 9, 11, 5, 6. And if I look at in my right-hand side column vector, B is -1, 3. So what is the vector equation A x? My x is going to be the two, A times xy equal B mean? Or let me write it like this, just suppose I write x with the arrow to be just xy. So ax equal b. What does this mean? So this is A is the matrix, 9, 11, 5, 6. This is the vector xy equals -1, 3. Right? If I do this matrix multiplication, this is 9x plus 11y, 5x plus 6y, that vector equals -1, 3. So if I have this equation, this says exactly this. But two vectors are equal. These are two column vectors. They're equal if their coordinates are the same. The first coordinates, 9x plus 11y equal -1. Second coordinates, 5x plus 6y equals 3. So I have this system of equations, which in vector form I can write like this, where A is the matrix of coefficients of the variables, and B is the column vector of the right-hand sides. This is just an alternate way of writing my equations. Right? So I can write equations like this, or I can write it in vector form like this. That's all we're saying at this point. I mean, is there a question about this? I mean, it's supposed to be, there's no real mathematical content yet. This is just, it's like, do you write the number 2 or do you write the word 2? They're the same thing. So this is one way of writing the system of equations. This is a second way of writing the system of equations. This is one way of writing 2. This is another way of writing 2. It's just, there's not a difference between these two yet.
Is it the same thing as linear equation?
Well, they're all linear. The whole course, our whole course is linear equations. There's nothing else in this entire course. Everything is linear equations. This is a system of linear equations.
Okay.
But the question that started the class was, how do we use these matrices to solve a system of linear equations? So I want to introduce one more matrix from a system of equations. If I have the system of equations A1, X1, A2, X2, up to A1, N, X, N equals B1, AM1, X1, AM2, X2, up to AMN, XN equals B sub M. I have this system of equations. I define the matrix of coefficients, but now I want to define what is called the augmented matrix associated with this system. So in this matrix, this is going to be a M by N plus 1 matrix. So this matrix will have M rows, one for each equation, and N plus 1 columns. So the first row will be the coefficients of the x's, A11, A12, up to A1n, but then we add the number on the right, B1. The second row will come from the second equation. A21, A22, A2n, B2, all the way down to the mth equation, AM1, AM2, AMN, B sub M. So this is the augmented matrix of the system. Okay? So if I look at this previous example, here I had these two equations and two unknowns. For this system, what would the augmented matrix be? Nine, 11 minus 1, 5, 6, 3. That's the augmented matrix for this system. Two equations, two unknowns, plus the right-hand sides gives me a 2 by 3 matrix. 2 rows, 3 columns. That's the augmented matrix. Now, how can we use this to solve a system of equations? You remember when we had a system of equations, we had 3 elementary operations on a system of equations. So you could, first of all, interchange 2 equations. You get a new system, but it's equivalent in the sense that it has the same solutions. If you interchange 2 equations, what does that do? How does your augmented matrix change? This corresponds exactly to interchanging 2 rows of the augmented matrix. If you start with a system of equations, if you interchange the first 2 rows and then write down the augmented matrix for the new system, it would be the original augmented matrix, but with the first 2 rows interchanged. So interchanging 2 equations is the same as interchanging 2 rows of the matrix. You can multiply an equation by a non-zero scalar. And if you do that and write down the corresponding augmented matrix, that corresponds to multiply a row by a non-zero scalar. And You can also add a multiple of one row to another row. And that corresponds exactly to add a multiple of one equation to another equation. You can add a multiple of one row to another row. And just as we can do sort of Gaussian elimination on a system of equations to solve the system, we can do the equivalent steps of Gaussian elimination on the augmented matrix to solve the system of equations. So let's just try and look at an example to try and make this easy. Or suppose we have this system of equations. X plus 2y equals 5. 3x plus 4y equals 6. So the matrix of coefficients of this system is 1, 2, 3, 4. But the augmented matrix, you add one more column, the 5, 6 column. So here we have two equations and two unknowns. This is the augmented matrix. How can we solve this system? Well, if we were using equations, we could leave the first equation fixed for the moment and subtract 3 times the first equation from the second. So you would take this equation, subtract this equation. 3x minus 3x is 0. 4x minus 6y is minus 2y. 6, I'm multiplying this by 3, 15. Sorry, I'm multiplying this by 3. Yes, multiplying this by 3, I get 15. 6 minus 15 is minus 9. What does that correspond to with the matrix? I have the matrix 1, 2, 5, and I'm subtracting 3 times the first row from the second. So this row minus 3 times this row. 3 minus 3 is 0. 4 minus 6 is minus 2. 6 minus 10. Sorry, 6 minus 15 is minus 9. Then I can multiply the second equation by minus a half. I will get x plus 2y equals 5. Multiplied by minus a half, I get y equals 9 halves. Or I could take this matrix and multiply the second row by minus a half. I would get 0, 1, 9 halves. Then I could leave the second equation fixed, but I could take the first equation minus twice the second. So x minus 0 is x. 2y minus 2y is 0. 5 minus 2 times this is 5 minus 9 is minus 4. Equivalently, I take my matrix, second row I leave alone, and I add minus 2 times the second row to the first row. I get 1, 0, minus 4. So these operations that I do on the equations to solve the equations, I can also do on the matrix. And this matrix corresponds to this system. This matrix corresponds to this system. In both cases, we've solved the equations, the solution, x equals negative 4, y equals 9 halves.
I have a question.
Yes.
Can you explain, please, the last matrix, the second row?
Here?
Yeah.
Well, it's the same as this.
Okay, you just dragged that down.
Right, so as I went from here to here, I didn't do anything to the second row, but I added I added the -2 times the second row to the first row. Or equivalently, I took the first row minus twice the second row, and that's how what changes from here to here is the first row. Right?
Okay.
Nothing else changed.
Professor, how you got x equals -4?
So if I multiply the second equation by -2, I get -2y equals -9. If I add it to this equation, the y's cancel. 2y minus 2y is 0. 5 minus 9 is -4. It's the same thing as saying plug 9/2 into this equation and you get x equals -4. This says that y is 9/2. If you plug that into this equation, x is -4.
Y equals 9/2. The 9/2 came from dividing by 2.
My
The sec-
-2. From here to here, I mean, I'm going step by step by step.
Mhm.
From here to here, I subtracted 3 times the first row from the second. I didn't change the first row. I subtracted 3 times the first row from the second. From here to here, I multiplied the second row by -1/2. From here to here, I added -2 times the first row to the second.
Can I see the bottom? Can you move the paper up? Yeah. The problem we did before is different from this one, right?
This problem,
Yeah, that one.
it's a different problem.
But they both system of linear equations, right?
Everything we do in this course is systems of linear equations. In one form or another. Linear algebra is linear equations.
Okay.
Right? Matrices, we use matrices, among other things, to solve linear equations.
Professor, is it coincidental that the left side of the augmented matrix ends up looking like the identity matrix, or is that
That's the
like
goal.
okay? So basically, every time you do this, you're looking to get the identity matrix as the left side.
Or as close to it as you can get. You can't always get it.
Okay.
But that's a very good observation that we ended up with this part of it looking like the identity. Now, suppose we had 2 equations in 3 variables. Suppose I had the system x plus 2y plus z equals 3, and 3x plus 4y plus 2z equals 2. And I want to try and solve this system. And I want to try and solve it using matrices. So for this, what is the augmented matrix? It's going to have coefficients 1, 2, 1. These are the coefficients of the variables. And in the second, from the second equation, the coefficients of the variables gives me 3, 4, 2. And then I write this numbers on the right-hand side as 3, 2. So this is the augmented matrix for this system. And what I want to try and do is put the matrix in what is called reduced row echelon form. And when it's in that form, you want like the first variable in the first row to be a 1. Well, it already is, so we're fine. And underneath it, you want to get zeros. So I have a 1 here. I like, but the only thing I'm allowed to do to a matrix is perform one of the elementary row operations. I can interchange rows. I can multiply a row by a scalar. I can add or subtract a multiple of one row from another. So I start off with a 1 here. That's good. That saves me some work. So I'm not going to change the first row now, but I want to get a 0 underneath it. The way I can get a 0 here is to subtract 3 times the first row from the second. So if I take this row and I subtract 3 times the first, I get 3 minus 3, which is 0. 4 minus 6 is minus 2. 2 minus 3 is minus 1. 2 minus 9 is minus 7. Okay. So how did I get from here to here? I add minus 3 times row 1 to row 2. That's how I got from here to here. I didn't change the first row, but I changed the second row. Now, in the second row, under the 1, there's a 0, but I want the first non-zero entry to be a 1. So I'm going to take the second row. What I'm going to do is, to get from here to here, I'm going to multiply row 2 by minus a half. So I'm not doing anything to the first row. If I multiply this by minus a half, I get 0, 1, a half, 7 halves. Okay. So I started with this augmented matrix. I multiplied the first row by minus 3 and added to the second, I got this. From this matrix, I multiplied the second row by minus a half, I got this. So now I have a 1 as this first non-zero entry in the second row. I'd like to get a 0 above it. So how can I get a 0 in the first row in this place? I can take the first row minus twice the second row. So in my next step, I'm not changing the second row. But to get a 0 here, I can multiply this row by minus 2 and add. 1 plus 0 is 1. 2 minus 2 is 0. If I multiply this by minus 2, I get minus 1 plus 1 is 0. If I multiply this by minus 2, I get 7, and add this and I get 4. So now I have this system of equations. And in this system, this has the following very nice property. The first number in the first row is a 1, and underneath it, everything is a 0. The first number in the second row that's non-zero is a 1, and everything above it is a 0. And whatever system of equations corresponds to this is equivalent to the original system of equations. What is the system of equations associated with this? It's x, 1 times x, 0 times y, 0 times z, x equals 4. What's the system of equations associated with this? Y plus a half, z equals 7 halves. So this says that or another way of saying this is, so x equals 4 and y is 7/2 minus 1/2 z. So if you have any solution of this system of equations, x, y, z, x has to be 4, z can be anything, and y has to be 7/2 minus 1/2 z. So this is like saying this is the vector 4, 7/2, 0, plus z times the vector 0 minus 1/2, 1. This is exactly what we would expect for this system of equations. If I let,
I have a question.
yes,
So, I kind of understand that you got in the second matrix, in the second row, 0, -2, -1, and -7.
yeah. Let me just double check to make sure I did my arithmetic right, because I think I did some arithmetical error somewhere. 1, 2, 1, 3, 3, 4, 2, 2. So I take 1, 2, 1, 3. If I subtract 3 times the first row from the second, 3 minus 0, 4 minus 6, 2 minus 3, 2 minus 9. Then I multiply the second row by minus 1/2. I get 0, 1, 1/2, 7/2. Then I add minus 2 times the second row to the first. I get, so the second row doesn't change, 0, 1, 1/2, 7/2. The first row becomes 1, 0, 0, minus 4. I knew there was a mistake somewhere. Minus 4. So x, y, z, so these are the equations. X equals minus 4, y plus 1/2 z equals 7/2, or y is 7/2 minus 1/2 z. So there should be a minus 4 here. So for this system of equations, we know for an inhomogeneous system, the solution is an affine space. So the solution L, the set of all solutions, is the particular solution minus 4, 7/2, 0, plus the set of all scalar multiples of the vector 0 minus 1/2, 1. So let me write down very carefully what it means for a matrix to be in row echelon form and reduced row echelon form. So a non-zero, and if you look at the notes, you will see this is on page 97 already. A non-zero matrix is in row echelon form if it satisfies the following properties. So there is a positive integer r. So the matrix is going to have r non-zero rows. Some rows of a matrix can be all 0. And you can have a matrix that looks like 1, 2, 3, 4, 5, 6, 7, 8, 0, 0, 0, 0, 0, 0, 0, 0. You can have a matrix where some rows are 0, okay? But a non-zero matrix is in non-zero means you can have some zeros in the matrix, but at least one coordinate is different from 0. So this is a non-zero matrix. A non-zero matrix is in row echelon form if there's a positive integer r and r positive integers k1 less than k2 less than k sub r, that satisfy the following properties. So let me just explain with an example what this means before I write down formally what it is. You have an m by n matrix, m rows, n columns. So you have the first r rows, and then the rest, r plus 1 up to m. So these are the first r rows, and these are the last m minus r rows. So in the bottom rows, it's all zeros. In the first row, it's 0 until you get to the k first column, and there you're going to have a 1. So in each row, for I going from 1 up to r, the coordinate in row I, column k sub I, is going to be a 1. So in row 1, column k1, there's a 1. In row 2, column k2, there's going to be a 1. And what else? In this first, everything before this k1 is a 0. In the second row, every coordinate before k2 is 0. The third in k3, it means in k1, in the third row, the first non-zero coordinate is going to be in column k3, and everything before that is going to be a 0. So these numbers k1, k2 up to k sub r tell you in what column the first non-zero coordinate will be in your matrix, and that first non-zero column and every non-zero row is going to be a 1. So as you move down the matrix from one row to the next, as you go across the row, the first number that's different from 0 will be a 1. And as you go from one row to the next, the 1 is moved to the right. These ones are moving over. Moreover, so that's what row echelon means. A matrix is an echelon form if it has this property. And it's reduced. So it's in reduced row echelon form. As you go across the row and you get to the first non-zero entry, which is a 1, in that column above and below it, there are only going to be zeros. Right? So if you look at column KI, and you go down that column, in row I, there's a 1, and everywhere else there's a 0. And as you go from column K1 to K2 to K3, that first non-zero 1 is going to be moving off to the right. So,
I have a question.
yes,
So this part to the right hand side, I didn't really understand it. I was trying to, listen, but I don't understand it.
I'm sorry, I didn't hear the last thing you said.
I don't understand the last part. So this diagram that you have on the right hand side, I don't understand it.
Okay, so I'm trying to describe what it means for a matrix to be in reduced row echelon form. So as you go across, the first non-zero number you come to is a 1.
Okay.
And in that column where there's a 1, everything else is 0. Okay? And then you have
Okay.
other stuff. Now, whatever it may be, we'll see. In the next row, as you go across, the first non-zero entry will be further to the right of the one in the first row. So maybe it's here. And everything else in before that one will be a 0. And in this one, everything above and below it will be a 0. Okay?
Okay, I
As you
understand.
go across the third row, you get zeros until you get to a 1. And that 1 will be to the right of the one in the row above it. And everything above and below this 1 will be a 0. Okay?
Got it.
And anything else can be whatever, and any row which is all 0 is at the bottom, because some rows will only have zeros in them. All right? So here we have 2 rows that are all zeros, but they're at the bottom. The rows that are not all 0, they're the first 3 rows. And let's say there's even another thing there. And these ones, as you move down the matrix from one row to the next, the ones are moving to the right. And what's above it, I mean, the other numbers could be anything. Right? So this matrix is in reduced row echelon form because, first of all, the 0 rows are at the bottom, the non-zero rows are above. And on the non-zero rows, the first non-zero coordinate's a 1, but as you go down the rows, the ones are moving off to the right. And wherever you do have one of these initial ones, everything else in that column is a 0. So this is a reduced row echelon form. And the effective way to solve a system of linear equations is to write the augmented matrix for the system, use elementary row operations, interchanging rows, multiplying a row by a constant, adding a multiple of one row to another, to put the matrix in reduced row echelon form. And this can always be done. And the result is unique. There's only one reduced row echelon form that you can get out of any given matrix. And when you write the system of equations that corresponds to the augmented matrix, that system of equations is equivalent to your original system, but you can use this to solve the equations. So I want to just do, I want to spend the rest of this period just doing examples of what I'm talking about. Okay. So this is the idea, first of all, of reduced row echelon form. Non-zero rows on top, 0 rows on the bottom. In each row, in each non-zero row, the first non-zero number is a 1. And as you move down the matrix, these initial ones move off to the right. And in any column where you have one of these initial ones, every other number is 0. So suppose we start with this system of equations. So here I have 3 equations in 2 variables. So what is the augmented matrix for this system? It's going to be 3, 13, 37, 1, 4, 13, 2, 14, 7. And I want to put, this is my goal, put matrix in reduced row echelon form by performing a sequence of my elementary row operations. Now, is there only one way of doing this? No. There are infinitely many ways of doing it. It's up to you how you do it. And the more problems you do, the better you'll get at making like more efficient choices for what to do. So, for example, in this matrix, all the rows are non-zero, at least to start. I want a 1 here. I want the first number in the first row to be a 1. Now, I could multiply the first row by a third. That would give me a 1 here. But to avoid some fractions, it might be easier to just interchange the first 2 rows. So in this matrix, I'm not changing the third row. But if I interchange the first 2 rows, the second row, 1, 4, 13, becomes the first row. And the first row, 3, 13, 37, becomes the second row. So now I have the first non-zero number in the first row is a 1. But I want to get everything below that to be a 0. So let's see, I have 1, 4, 13. Let me make this a 0. So at this step, I'm not changing the third row. How can I get a 0 here? I can take the first row, I can take the second row, minus 3 times the first. 3 minus 3 is 0. 13 minus 12 is 1. 37 minus 39 is minus 2. So the way I got from here to here was I interchange rows 1 and 2.
I have
How
a
did I
question.
get from here? All right, is there a question about any of this so far?
Yes.
Go ahead.
So when you said 37 minus 39,
Yes?
where did you get 39 from?
Okay, so how do I get from here to here? I didn't change the first row and I didn't change the third row, but what I did was I subtract 3 times row 1 from row 2. So let me do this little calculation over here. Here's row 2, 3, 13, 37, right? Right, this is my row 2. This is row 1. If I multiply row 1 by 3, I get 3, 12, 39. When I subtract, I get 0, 1, 2. 0, 1, minus 2. So here I have my second row, 0, 1, minus 2, which I obtained by subtracting 3 times row 1 from row 2. Okay, so 39 is 13 times 3.
Thank you.
Now I want everything in this first column under the 1 to be a 0, so I have to get rid of this 2. So I have my first row, my second row. I can get a 0 here by subtracting twice row 1 from row 3. 2 minus 2 is 0. 2 times 4 is 8. 14 minus 8 is 6. 2 times 13 is 26. 7 minus 26 is minus 19. Actually, sorry, I want to I'm gonna make one small change because I want this to be like the example in the notes. In the notes, this third equation was 14 here. So if that's 14, this is 14. This is 14. I'm not changing anything, 14. And when I subtract 2 times the first equation from the second, 14 minus 26 is minus 12. Okay. So to get from here to here, I only changed the third row and I subtracted 2 times row 1 from row 3. Okay. So now my first number in row 1 is a 1. My second number in row 2 is a 1, and it's to the right of this one. So these ones, as I go down the rows, are moving to the right. But now I want to get a 0 above and below this 1. So to get a 0 here, I'm not changing the second row or the third row yet. I have 0, 1 minus 2, 0, 6 minus 12. If I take the first row and I subtract 4 times the second row, I get 1 minus 0, 4 minus 4, that's 0. 13 plus 8 is 21. Right? This is minus 4 times row 2 added to row 1. So I have a 0 here. Now I want a 0 here. So I'm not changing the first row. I'm not changing the second row. But to get a 0 here, I subtract 6 times the second row from the third. 0 minus 0 is 0. 6 minus 6 is 0. Minus 12 plus 12 is 0. So now I have this matrix, and see, this matrix is in reduced row echelon form because there's 1 0 row, it's at the bottom. And for the non-zero rows, the first non-zero entry is a 1. The ones move to the right as you go down, and above and below those ones are only zeros. Now this corresponds to a system of equations. The system of equations corresponding to this is x equals 21, y equals minus 2. So we solved our equations. Yeah, we solved our equation. We took our initial system of equations, wrote down the augmented matrix, put it in reduced row echelon form. This is the equivalent system. And let's just check that this actually does solve our equations. 3x plus 13y, 3 times 21 plus 13 times minus 2 is 63 minus 26 is 37. That checks. X plus 4y is 21 plus 4 times minus 2 is 21 minus 8 is 13. That checks. 2x plus 14y, 2 times 21 plus 14 times minus 2 is 42 minus 28 is 14. That checks. So that's the solution of my system of equations, which I found by taking the matrix and putting it in reduced row echelon form. That's kind of nice. So let me keep doing some problems because I mean, you have to learn how to do these kinds of algebraic operations on matrices to solve a system of equations by putting the matrix in reduced row echelon form. Maple will do this for you, but you have to know how to do it by hand. So in the exercises, they're systems of equations, and you're asked to solve them by using elementary row operations to put the matrix in reduced row echelon form. So let me start with some of these exercises. 1A, it's always a good place to start. 9x minus 4y equals 1, minus 11x plus 5y equals 3. So what is the augmented matrix? It's going to be 9 minus 4, 1, minus 11, 5, 3. Now, unfortunately, you have to know fractions. Right? Can't avoid that, I'm afraid. So let's see. I want to have a 1 here. So I multiply the first row by a 9th. So the second row is the second row. If I multiply this by a 9th, I get 1 minus 4 over 9, 1 over 9. Then I want to get a 0 here. So I leave this first row by its alone. And I add 11 times the first row to the second. So 11 minus 11 is 0. If I multiply this by 11, I get minus 44 over 9. 5 is the same as 55 over 9. So I have minus 44 over 9 plus 55 over 9. So I think that's 11 over 9.
A question.
Yes.
Wouldn't 5 be 45 over 9?
Oh, sorry, 45 over 9. Well, sorry, it is. Let's see. So I have minus 44 over 9 plus 5, which is 45 over 9, which is 1/9. Thank you. It's going to make it easier. 1/9. And minus 11 over 9 plus 3. 3 is the same as 27 over 9. So it looks like this is 38 over 9. Let me just double check. 11 minus 11 is 0. 5 minus 44 over 9 is 1 over 9. 3 plus 11 over 9, 27 plus 30. That looks like it's okay. All right, next step, I want to get a 0 here. So my first row, 1 minus 4 over 9, 1 over 9. And I multiply the second row by 9, I get 0, 1, 38. And then I want a 0 there. So I have 0, 1, 38. I multiply the second row by 4 over 9, and I add. So I get 1 plus 0 minus 4 over 9 plus 4 over 9. And then 1/9 plus 4/9 times 38. So 1/9 plus 38 times 4 over 9. Let's see, 38 times 9, that's 72. 9/8 are 72. 9/3 are 27. what is this? I'm adding 4 ninths times this row, so it's 38 times 4 ninths plus a ninth. 38, 4 times 38, 4 eighths are 32, 302 over 9, which is, this is 9 over 9, so this is 311 over 9. Somehow, might be it's correct, but let me just double check all my arithmetic again. 9 minus 4, 1, minus 11, 5, 3 is my matrix. Multiply this by a ninth. 1 minus 4 over 9, 1 over 9, minus 11, 5, 3. Add 11 times the first row to the second, I get 0. 5 minus 44 over 9 is 1 ninth. 3 plus 11 over 9 is 27 over 9 plus 11 is 38 over 9. So this looks okay. Then I multiply the second row by 9, I get 0, 1, 38. And this is minus 4 ninths plus a ninth. I add 4 ninths times the second row to the first, gives me a 0 here. And what goes in over there is 4 ninths times 38 plus a ninth. 4 eighths are 32. Oh, this is all, my arithmetic's completely off. 4 times 38, this is 9 over 9 is 1, plus what over 9? 4 times 8 is 32. 4 times 3 is 12, plus 3 is 15. So this is 161 over 9. Yeah. So something is completely, it might be off here, I don't know. Something is wrong. So when something is, and the reason I know is wrong is this would correspond to the system of equations x equal 161 over 9, y equals 38. And let's see, 9 times 161 over 9 is 161, minus 4 times 38 is 152. Oh, no, this might be right. Let's just check. 9x minus 4y is 9 times 161 over 9 minus 4 times 38. This is 161. What is 4 times 38? 32. 152. This is 9. It's not 1. So somewhere, somewhere I made a mistake here. If this were 38 over 9, it would work. So all I can do is keep checking. 9 minus 4, 1, minus 11, 5, 3. So I get 1 minus 4 over 9, 1 over 9, minus 11, 5, 3. Then I add 11 times the first row to the second. 11 minus 11 is 0. Minus 44 over 9 plus 45 over 9 is 1 over 9. 11 over 9 plus 3 is 38 over 9. Then I get 0, multiplying the second row by 9 gives me 0, 1, 38. That's this. And then adding 4 ninths times this row to this row. 4 times 38 is 152 over 9. 152 over 9 plus a ninth. This is a plus 1/9. That's equal to 153 over 9. And 9 into 153 goes exactly 17 times. Oh, wow. So this is a 17. So the solution of this system of equations should be x equals 17, y equals 38. So let's check. 9x minus 4y is 9 times 17 minus 4 times 38. 9 times 17 is 153. 4 times 38 is 152, and that's 1, so that checks. Minus 11x plus 5y is minus 1117 plus 5 times 38. Right? And minus 11 times 17 is minus 187, and 5 times 38 is 190. 190 minus 187 is 3, so it works. So we solved the problem. Right? Sometimes it takes a while. So I'm solving a system of equations by writing the augmented matrix and putting the augmented matrix into reduced row echelon form. And the solution space W consists of just a single vector, 1738. Right? There's that affine space. Let's do another problem, one more. It'll take up the rest of our time, but it's worth trying to get this done. Suppose I'll look at 1D. So we have 3 equations and 3 unknowns. X plus 4y plus 3z equal 2. 2x plus y plus z equals 3. 3x minus 2y minus z equals 4. So the augmented matrix corresponds to the system as a 3 by 3 matrix. 1, 4, 3, 2. 2, 1, 1, 3. 3 minus 2 minus 1, 4. This is the augmented matrix. 1, 4, 3, 2. 2, 1, 1, 3. 3 minus 2 minus 1, 4. So I want to get zeros below the 1. So I can take the second row, leave this third row unchanged. Subtract 2 times the first row. 2 minus 2 is 0. 1 minus 8 is minus 5. 1 minus 6 is minus 5. Let's see. 1 minus 8 is minus 7. Better get that right. 2 minus 2. 1 minus 8. 1 minus 6. 3 minus 4. And I want to get a 0 here. 1, 4, 3, 2. 0 minus 7 minus 5 minus 1. You get a 0 here. I add 3 times, subtract 3 times the first row from the third. 3 minus 3 is 0. minus 2 minus 12 is minus 14. Minus 1 minus 9 is minus 10. 4 minus 6 is minus 2. So I have 1 and then zeros. Now I want to get a 1 here and zeros above and below it, but I'm allowed to do any order of operations I want. And I notice that the third row is twice the second row. So if I take the third row minus 2 times the second row, I'll get zeros right away in the third row. And that makes my computations a little bit easier, right? I just noticed 7, 14, 5, 10, 1, 2. This row is twice that. So minus 2 times this plus this gives me all zeros. Okay. Then I want a 1 here. So I have 1, 4, 3, 2, 0, 0, 0, 0. Multiply this row by minus a 7th. 0, 1, 5 over 7, 1 over 7. And then I want a 0 here. So I have 0, 1, 5 over 7, 1 over 7, 0, 0, 0, 0. Minus 4 times the second row from the first, or the first minus 4 times the second. 1 minus 0, 4 minus 4. Minus 4 times this, 3 minus 20 over 7. This is 21 over 7, so this is 1 over 7. 2 minus 4 over 7. This is 2 is 14 over 7 minus 4 over 7 is 10 over 7. So now this matrix is in reduced row echelon form. There's a 0 row at the bottom. In the non-zero rows, the first entry is a 1, the 1 moved to the right, and zeros above and below. And the system of equations corresponding to this matrix is x plus 1/7 z equals 10 over 7, y plus 5/7 z equals 1 over 7. So for any solution, once I pick my value of z, x is 10 over 7 minus 1 over 7z, and y is 1 over 7 minus 5 over 7z. So x, y, z is a solution if for any z, x is 10 over 7 minus 1 over 7z, and y is 1 over 7 minus 5 over 7z, which is 10 over 7, 1 over 7, 0, that vector, plus z times the vector minus 1 over 7 minus 5 over 7, 1. So this should be a particular solution of the equations, and this should be a solution of the homogeneous system. Let's just check 10 over 7, 1 over 7, 0. In the first equation, x plus 4y plus 3z is 10 over 7 plus 4 over 7 is 14 over 7 is 2. That works. 2x plus y plus z is 20 over 7 plus 1 over 7 is 21 over 7 is 3. That works. 3x minus 2y minus z is 3 times minus a 7th minus 2 times minus 5/7. That's minus 3/7 plus 10 over 7 is 7 over 7 is 1. Oops, that doesn't check. That's 1. It's supposed to be 4. Minus 1/7 minus 5/7. Minus 3/7 plus 10/7 is 1. Good. So somewhere there's some arithmetical error hidden away, which needs to be discovered. But the method is the method. And the only way to learn the method is to work these problems out. They can take a lot of time. Make sure when you finish, you check. And with high probability, the check will show that you made a mistake, which is actually a good thing because it forces you to go back and step by step examine what you did until you get the result. And if you want to know the answer, and if you have Maple, Maple will tell you the answer. Maple will solve all these equations, and you can check. Okay, that is all we're doing.
There's no class on Monday. But there's their class on Wednesday, right?
Yes, next Wednesday there's definitely class.
Okay, thank you.
So it's 1 week until the next class. Today is Wednesday, and then next Wednesday. Okay, all. Have a good weekend. Bye.
Thank you.